Hello, my name is Tim Goodwin. I'm a PhD student at UC Santa Cruz. And today I'm going to be talking about Kubernetes controllers and how we can compose them together to build higher level platform abstractions, the headaches involved with this process, and a new simulation testing tool that I've been developing as part of my research to make this process a lot easier. So when Kubernetes started off about a decade ago, it was about orchestrating containers. But today we can do way more than that. We can use Kubernetes to manage a whole variety of cloud infrastructure. Frameworks like Crossplane let us use Kubernetes to manage infrastructure that's even external to the cluster itself. So how did we get from a better way to run containers to a universal control plane for anything we want? Well, the answer lies in the power and generality of the underlying model that Kubernetes uses, in which we describe some desired state of our system in terms of logical resources, and then the system is going to continuously reconcile that state with controllers. So of course, this model works great for orchestrating containers, but it generalizes far beyond that. Pretty much anything that can be described declaratively and reconciled continuously, we can manage with Kubernetes. And Kubernetes makes it really easy to apply this model to new use cases through the extensibility of its API. So to add new functionality to the platform, say for example, we want to teach Kubernetes to manage some database that's called like foo-db. Well, we can simply define a new resource type, or CRD, for foo-db. And then we're going to implement the behavior of that resource with a custom foo-db controller. So resources and controllers give us the building blocks to make custom control plane functionality for whatever we want. And it's very powerful to be able to add a new resource type for something like foo-db. But there's even more power in our ability to compose resources together to create higher level abstractions. So say we're in some software organization and we're constantly writing applications that all need to talk or have some network endpoint, and they all need to store some data, maybe using foo-db. Of course, with Kubernetes, we can deploy this using a service, a deployment, and our foo-db custom resource. But we could also abstract away these architectural details using a higher level composite resource type. So as platform engineers, we could add another resource. Maybe it's something that we'll call AppStack. And this is going to bundle a service, a deployment, and this foo-db custom resource into a single, simpler contract that application teams can then consume. And we're also going to write another controller to implement AppStack, and this controller is going to handle fanning out the AppStack resource into the lower level sub-resources, which will then be in turn handled by their respective controllers. So it's this composition technique that lets us raise the level of abstraction. And this is what enables Kubernetes to function as a platform for building platforms. And behind the scenes, this composition process amounts to the custom controllers that we write interacting with other controllers in the system through updates to resource state to collectively fulfill these higher level abstractions that we're designing. But this composition process can be really hard to get right. For one, writing a custom controller can be a tricky and error-prone process. And when we're adding new controllers into the system and composing them together with other controllers to build these increasingly sophisticated abstractions, these controllers and the way that they interact with one another can become a huge source of complexity. And when something goes wrong in these interactions, it can be a huge headache to debug what's going wrong. So the rest of this talk is going to be about these challenges and how we can use simulation testing to solve some of these challenges. But before I go on, I have one slide on controllers, just in case anyone here in the audience isn't familiar. So a mental model of a controller is just some process running in the control plane that's going to manage the state of some resource type with respect to some desired specification. And it does so by subscribing to a stream of change events for that resource type from the API server. So when a change event comes in, our controller is going to react to that change event, get the current state of that resource, compare it to some desired specification of that resource, and perform some operations, again with the API server, to drive that actual state towards some desired spec. And it's going to do this continuously. Each time a change event comes in, it'll run the same reconcile routine, And if nothing needs to be done, this routine will just return early, as no actions are needed. But expressing our controller logic in terms of a reconcile loop is actually kind of tricky. So to illustrate why, let's return to this hypothetical foo-db custom resource example from earlier. So with a database like foo-db, we're running some stateful application on Kubernetes. And we're probably going to use a stateful set to do this in conjunction with some Kubernetes service. So our reconciliation logic might look something like this. At a first glance, it's pretty simple, but there are some subtle issues here. So consider if the controller crashes right after it creates the stateful set. Then when it comes back up and reruns its reconcile routine, we're actually not going to enter this conditional because the stateful set already exists, and the headless service is never going to get created. This means that the pods backing the stateful set aren't going to be able to find and talk to each other. So what we want to do here is decouple these create operations. But this is almost correct, but there's still another issue down at the bottom of our routine in this seemingly innocuous updates to the foo-db resource status. We might just be labeling it as initialized to reflect that we have already taken the actions to create its sub-resources. But if we look closely, we'll notice that in each invocation of this reconcile, we're always issuing an update command to this foo-db resource no matter what. And because this controller is subscribing to changes to the foo-db resource type, each update is going to re-trigger the reconcile to run, another update will be issued, and so on. So this is going to create an infinite stream of update events. And in practice, this stream of update events can put a lot of strain on the API server and potentially cause more problems. So we only want to issue an update if something actually changed. A common way to solve this problem in writing reconcile routines is to take some copy of the foo-db resource at the top of our routine, let our business logic flow through, and then at the very end, we're going to compare the in-memory state of our foo-db resource to that copy that we took earlier, and only if they're different will we issue this update command. So in this side-by-side comparison, you can see that the business logic is pretty simple, but there's a lot of things that you need to watch out for to ensure that this business logic runs soundly within a reconcile loop. And unfortunately, let's see. Sorry. Unfortunately, things get a lot harder when we start reasoning about the composite logic of multiple controllers in our control plane. So consider what is admittedly an extremely contrived example on the right here, where we have our foo-db controller, and then maybe some other controller that's also monitoring and potentially managing some properties of this foo-db resource type, where they're both managing this owner attribute. Well, if these two controllers are deployed together, they're going to start fighting over the value of this owner resource attribute. So one controller is going to update it to one thing, that'll trigger the other controller to do the same thing, and so on. So now we have another chain of never-ending updates, although this time there's two controllers participating. And a point that I want you to take away from this really contrived example is that both controller code in isolation, it might be sound and stable, it's idempotent, but it's only when we combine them together that an issue manifests. So these types of cross-controller issues can manifest and be triggered by a variety of factors. Of course, a code change. They can come up when we change something about how we're modeling resource relationships in our cluster, or configuration changes, et cetera. And they might only manifest under certain conditions, so they can be very hard to anticipate at development time. So there's this whole class of issues lurking in the way that controllers interact. And unfortunately, interactions are everywhere. So even in some simple scenario like creating a deployment, there's a whole lot of controllers interacting behind the scenes to fulfill that overall reconciliation process. And you can imagine in some more complex scenario, when we're writing our own controllers and composing them together with other third-party controllers that we might be pulling off the shelf, we're introducing a lot of places for potential interaction issues to crop up. And one thing that we can also see in this diagram is that when controllers interact, they don't do so directly. In the control plane, everything is loosely coupled and asynchronous. They're actually interacting through updates to shared resource state. And this means that when we're trying to reason about what's going on when something goes wrong, it can be really hard to figure out exactly where the issue is. So to that point, debugging these types of things is not a great experience. If there's some issue, we might go to our controller, the pod for the controller, look at the logs, pull up the same thing for a related controller, and try and mentally correlate how what one controller is doing is kind of indirectly affecting what another controller is doing. And throughout this process, we might need to reason about how the cluster state is evolving or how this state is affecting downstream controller behavior. And because these types of issues can reproduce in very specific and maybe fleeting conditions, that makes our overall debugging process even harder when there's a reproducibility challenge. So better observability would surely be welcome here, but it'd be really great if it were easier to catch these types of issues before we deploy our custom control planes in the first place. So that's where a simulation testing tool that I've been developing comes in. It's called Kamera, of course, with a K. And Kamera helps us reason about the correctness of our custom control planes by comprehensively testing the ways that controllers can interact. And for a given reconciliation process, Kamera is going to show us all of the controller actions that went into that process. So if there's some issue, we can understand exactly what's going on to create it. And lastly, it's going to do this all efficiently using simulation. So I'll first talk a little bit about the design of the simulation tool, and then I'll talk about how we're going to use simulation to test our control planes. So our goal is to test control plane behavior, which means that we care about the composite sum of all of our controller code and how that code is affecting resource state. But to test this code comprehensively, we have to explore a lot of different reconciliation scenarios, and exploring all of these using an actual cluster is going to take a lot of time. So we're going to speed things up by just simulating the rest of the cluster. And to do that, we can exploit the fact that controllers all interact with the rest of the system through the same access pattern, namely through the API server. So if we just swap the API clients that controllers use with something that looks like an API client, we can easily simulate the rest of the cluster without controllers knowing about it. So that's the core idea behind our simulation design. We're going to keep our controller code and the resource state and simulate the rest. And we do this by interposing at the API client interface. And in developing Kamera, I've actually built this around the controller runtime client interface. So if you have controller runtime implementations, you can wire them up to this tool without any additional code changes. Lastly, we're doing this all in one process, as there's no cluster involved. And what this means is that we can do this type of testing locally, we can run it alongside our unit tests, or easily run it as part of our existing CI/CD pipeline. OK, so that's the architectural strategy for our simulator, but how are we going to actually go about using this to test control plane behavior? So to explain how, I'll first need to overview how we're going to model the execution space of reconciliation. So in the most abstract sense, we can think of our Kubernetes cluster as some system in some state S. And then when a controller reconciles, it's going to transition that system into some new state. And it does so by performing some collection of actions or effects within a given reconcile invocation. And when a controller makes these effects, we can use knowledge of which resources, which controllers subscribe to determine which controllers are going to be triggered to reconcile by the changes in any given reconciliation. So in this case, some controller may have created a replica set. We know that in the resulting state, that's going to trigger the replica set controller to reconcile. And in Kamera's simulation framework, we're going to directly incorporate this notion of pending reconciles into our overall model of the state of the system at a given point in time. So in Kamera, the state of the system consists of the resource contents, as well as the controllers that have been triggered to reconcile by the transition into that resource state. So that's how we're going to represent state. How are we going to use it to simulate the reconciliation process? Let's revisit this example where we are reconciling the creation of a deployment. So in our simulation, we're going to start out in some state S, where some user has just created a deployment. It's now in the cluster's resource state, and we know that the deployment controller is about to reconcile. Our simulation framework is going to go into that pending reconciled set for the state, take out the deployment controller, and invoke its actual reconcile routine on the contents of S. So the deployment controller is going to see this deployment, it's going to create a replica set, and the system is going to transition into some new state, which contains this replica set. And we know that the replica set controller is subscribing to replica set changes, so that controller is going to show up in the pending reconciled set of this new state. And maybe the deployment controller is also going to update the deployment to reflect its status as progressing because the replica set has been created. That means the deployment controller is also going to wind up back in the pending reconciles set of this new state. And in the next step, we're going to select one controller from this pending reconciles set from state S prime. Say we select the deployment controller again. Now when the deployment controller reconciles, it's going to see this deployment in this progressing state. It's going to see this replica set. And it's going to decide that it doesn't need to do anything. The state is already as it expects. So the system is then going to transition into another state, S double prime. But note here that the resource contents between S prime and S double prime are the same. The only thing that differs is the set of pending reconciles. And in a camera simulation, we treat these two states as distinct. This process will continue. The replica set controller is going to go. It'll create some pods. Then the scheduler is going to get involved. It's going to create some pod bindings. Eventually, the pods will start running, and status will propagate back up to the deployment. It'll become available, and at a certain point, we stop. Well, when we stop, it means that our cluster state has converged. And the way that we represent that in the simulation is with a state that has an empty pending reconciled set. So what this means is that we're in some state where every controller that has stake in the contents of that state has observed those contents and decided that nothing needs to change about it. So that's how we model convergence in this simulation. Of course, convergence is just what we hope happens, but it's ultimately up to the soundness of our control plane logic to ensure that it actually does happen. If there's some non-idempotency issue or some update cycle among the controllers in our system, the simulation is going to keep going on indefinitely until we exceed maybe some threshold of simulation steps and conclude that there's got to be some issue somewhere. And in a real cluster, this can amount to putting serious thrash on the API server, maybe to the point of it toppling over, in which a bunch of even worse issues are going to happen. So it's really great that we can catch these types of scenarios in simulation. Another undesirable outcome that we want to use this execution model to watch out for is non-deterministic convergence. So if we go back to this happy path example where we did converge, you may have noticed that when I was stepping through it while we were in state S prime, I kind of arbitrarily selected that the deployment controller is going to go next when there were two pending reconciles in that set for that state. But theoretically, the replica set controller could have been the one to go next. So if our control plane logic is sound, it actually shouldn't matter who goes next, because Kubernetes in reality doesn't enforce any ordering among controller reconciles. So in our simulation, we can imagine a parallel execution branch where instead the replica set controller went first, and then the deployment controller. The process continues again, and then eventually will converge, presumably. And in this scenario, we now have two converged states. Well, if the contents of these two converged states are the same, that's fine. It just means that there were multiple ways to converge, and we can expect that from an asynchronous system like Kubernetes. But if their contents are different, that means that somewhere along the way, there was some ordering sensitivity, or in other words, a race condition, in our reconciliation logic. And what this means is that our reconciliation outcomes are going to be non-deterministic. So this is another undesirable outcome that we can detect using the simulation framework. But as a testing tool, we don't want to just detect when these undesirable outcomes happen. Ideally, we could go out proactively finding them and shore up the exact circumstances in which they occur, or verify that they won't happen. And to do this, we can use our execution model to comprehensively search every possible execution path and check for properties of interest like stable convergence. So this is a style of software testing called model checking, where we have some execution model and we want to exhaustively explore the space of all possible states that our system can enter into to verify that certain properties that we care about always hold. So in the context of reconciliation, we want to ensure that, for one, we do converge to the same place, and that we do so, no matter the ordering of steps we take to get there. And to do that, we're going to explore every possible execution path among controller reconciles. We're going to track and compare the converged states that we find along the way. And we're going to do this up to some max depth. So to describe this visually, it's effectively a big graph search. And in the happy path case where our code does converge, it'll look like us starting out at some initial state. A graph fans out below that, but then will ultimately fan back in to some single terminal node. In the case where there's a race condition somewhere in our control plane, the graph will have multiple terminal states stemming from some branch somewhere in that graph. And then in the case where we don't converge, or there's some update cycle that can manifest under some condition, there'll be some path that keeps going until we hit some maximum depth limit that's something that we've pre-configured. And so far I've been talking about this convergence property as it's pretty fundamental to the concept of state reconciliation, but we can in theory use this technique to specify and verify arbitrary properties in terms of cluster state that we might care about. So I have a short demo prepared. As part of my research, I've been trying to use the simulation testing framework to find new bugs in open source custom control planes. And one of them that I've been studying is the Knative serverless runtime. If you're not familiar, Knative is a popular Kubernetes-based serverless platform that uses this controller model to implement these higher level serverless abstractions. And I now need to navigate some tricky display stuff. So I'm going to kind of go like this so I can see what's going on. One sec. Whoops. Does that say Vim? Sorry, I really should have figured this part out first. OK, yeah, so I wanted to show you kind of what this code with Kamera looks like. I'm going to be brief, but pretty much what I'm trying to illustrate is that a camera simulation is just a Go program. Sorry, this is not. Where we're wiring up actual Knative controller implementations. What we're also doing is teaching Kamera which Knative controllers subscribe to which Knative resources. And then finally, we're configuring some top-level initial state. So here we're looking at a Knative serverless service. The starting state that we're going to be simulating is like some user just created a Knative service, and we want to see how that reconciles. OK. I'm now going to run the file that I just showed you. Hold on, I need to actually go back there and see what's going on. OK, so I'm going to kick off the simulation process. It's effectively executing a big graph search all in one process on my local machine, invoking all of the Knative controllers, seeing all the ways that this serverless Knative service can be reconciled. And this overall process typically takes a couple of minutes, so I'm not going to stand here and watch and wait for it to finish. But I've designed the tool to so that you can exit early, and it'll kind of show you the incremental execution paths that it's explored. So I'm going to Control-C out. We're going to drop into some terminal interface where we've identified that we found one converged state. So in this situation, there's no bug in Knative's code. It's just kind of showing how this convergence process happened under simulation. So down in the bottom, we can see the contents of the cluster state. The very bottom entry is that initial Knative service we started with, and we can see that the Knative control plane has created a bunch of other services that fulfill that serverless service abstraction. And then we can go into the converged state and look at all of the execution paths that we found to that converged state. And then if we explore one of these paths, what we get is what looks like a stepwise debugging interface, where on the right-hand side, we can see all of the controller reconciles that happened as part of this execution. And for each reconcile, it lists the number of changes or effects that the controller performed. Down in the bottom right, we can see exactly what those effects were. And then up top, we can see the contents of the cluster state after that reconcile completed. So what this lets us do is kind of step through each reconcile and inspect in a granular way how cluster state is evolving. I'm trying to find a good example to show. The next feature I want to show is that for each effect, we can actually go in and inspect at like the YAML level exactly what that controller did. So here, the deployment controller is updating some status conditions for this deployment type. I think it says it's adding a progressing status condition and setting that to true. OK, so that is my demo. And that's also where I'm going to conclude my talk. So to summarize, today we learned about how this pattern of composing controllers is what gives Kubernetes a lot of power to let us create these higher level platform abstractions. But the process of doing this composition can be really tricky and really hard to debug. So my simulation testing tool, Kamera, makes it easier to test controllers in the ways that they can interact. And it does this using simulation and a software testing technique called model checking. Specifically, it's verifying the soundness of our control plane by checking for deterministic convergence. And notably, it works on the same controller code that we'll actually be deploying into our system. And one last point that I wanted to make is that this currently is open source. It's on my GitHub. But this is like research grade software. What that means is it's not at all anywhere close to production ready. And one of the challenges of building a tool like this, which is very focused on platform engineering use cases in an academic context, is it's been hard to get feedback from people who are actually struggling with these problems in the real world. So if you think that this tool might be useful to you or you want to try it out, please get in touch. It would really help the development of this project. My homepage is discrete events, and there you can find my contact info. So I would be so thrilled to work with you and have you try it out and learn about the problems that you've been facing building custom control planes. So that's my talk. Thanks so much. The QR code is for session feedback, and I'll now take questions.
Hi, okay, thank you very much. It's a great talk. I have a bunch of questions. So first of all, if I understand correctly, the state, when you are generating this DAG, it's based on the order of the reconciliations.
Yes.
Yes, so shouldn't be that also consider the API interactions within a one reconciler, so simulate the case that two reconcilers running in parallel.
Exactly. So that's something that I wanted to fit into this talk, but I cut for time. But in addition to kind of exploring the order of controller reconciles, this tool can actually explore the order of controller cache update events. So you can kind of simulate the concurrency issues between controllers learning about some state update through their watch stream. But as you can imagine, that adds another branching factor to this graph that we're exploring. So that type of analysis becomes much more expensive.
Okay, just very quickly, second one. We've been doing something like this, but regarding testing, the Kubernetes API sometimes modify the resource, and just some samples like managed fields from server-side apply adds there are sensible defaults which might be changing, and other than that, which might impact the end resource in the API server. Is there a way to?
Yeah, that's a good call out. It's an issue with the simulation testing approach where we have to kind of faithfully mock out the behavior of the API server because we're simulating it away. So there's kind of like a long to-do list of things I've had to kind of empirically find that we're missing and go and add back in.
Okay, and just one more. To make it language independent, for example, use for Java operators and other stuff, would it be possible to implement this as a service where we still do watches for the informers, and we just decide where to propagate the event to which informer, to which controller, and running as a kind of a service?
Yeah, definitely. So early on, I was experimenting with, like, not fully removing the cluster, but using Quack to kind of just remove the container part of, like, we don't want to wait for containers to spin up just to test controller logic. So we could build something like that, but right now it's there's like a Go program.
Thank you.
Thank you.
Really nice talk. I'm curious if you can talk a little bit more about like how you do your graph search. Like how do you decide which paths to go down? Like which things are most likely to lead to bugs, I guess?
That's a great question, and a huge problem in this entire class of software testing in general. It's called the state space explosion problem. So the simple answer to how do you do the graph search, right now it's just a depth first search that'll time out at a certain depth. But as you make a great point, there's a lot of places that we're searching that are probably less interesting. So future research directions here involve developing heuristics to kind of guide or spend more time in areas of the graph where bugs might be more likely to manifest. But there's not currently like implemented strategies for that.
Hi, I have a CRD, for example, and there's a bunch of different services or controllers that are constantly watching that CRD, and there's a certain series of events that happens, and they all modify that CRD. Is this something that I could use to test that, like all these different paths? Because each service can do different things, and it updates that CRD. So they're all hitting it from different angles.
Do you mean service in like the Kubernetes terminology, or like an external?
Yeah, like so I have different controllers.
Okay.
That each modify that CRD. Like they do something to it. They do something and then they update the CRD, and then the next service is watching for certain events to happen. And based on those events of what previously happened, it does a different thing.
Oh,
and
yeah.
It updates that CRD.
Absolutely. I mean, I think it boils down to a concurrency issue among how your controllers are operating on the CRD. And this would be a perfect use case for that type of problem.
Is this something that I would run locally and that like on my laptop?
Yeah.
Like as I'm writing that controller code, I can test it before I deploy
Exactly.
it.
So that's kind of the idea behind doing this all locally, is you can keep it in the development feedback loop before you even commit or even deploy to a test cluster. Is kind of
I see.
my vision here.
So I don't actually have to have a cluster running on my laptop
Exactly.
while I'm writing my controller code, because I have a bunch of different controllers basically.
Yeah, like you don't even need to be running like a kind cluster on your laptop. You can just run a Go process.
That's interesting. Okay, cool. Yeah, I'm gonna check it out. Yeah.
Cool. Thanks so much.
Very nice talk, and very good progress. Have you thought about issues around reconcile side effecting or external services? So a lot of things like in bare metal Kubernetes and things like that, they're dependent upon external services that are actually watched for state changes, as well as I've noticed a common pattern in controllers now where they'll do things like, yeah, just let's reschedule in 5 seconds and see what's changed.
Yeah, so two great points here. With regard to external services, there's a trade-off between the fidelity of your simulation and the simplicity that you can achieve by mocking things out. So what I didn't point out in my demo is that I actually have mocked out the kubelet, for example. I just have this kind of synthetic stubbed out controller that will transition a pod through its lifecycle events and eventually assign it some random IP to reflect that it's been scheduled. But that's not necessarily exactly how some container interface is going to work in reality. So these are things that we need to be aware of when we're using these simulation testing techniques. And then your second point, it just slipped my mind. Sorry.
The common pattern that seems to be emerging in controllers of issuing the restart, reschedule.
Oh, yes, yes, like
pattern.
the kind of re-queue after 5 seconds pattern. That's actually a great point, and it's something that I'm trying to develop to test Knative, but at a high level, you could think of a re-queue with respect to some physical time amount as just, in the simulation, we'll just throw it back into the pending reconciles queue of the next state. But to virtualize physical time, we need more sophisticated software testing techniques. So there's kind of ways of using like big step or small step time intervals to kind of exercise if you have some conditional logic around some like call to like time.now, exercising both branches of that conditional statement without actually using a clock.
Great talk, and it's just fantastic actually to see distributed systems like depth first. I'm like, oh, that's actually is needed. So I guess leak code is actually useful. So I was like, okay, I accept now. But a very simple question is, I go to your repo and I'm like, all right, I want to play with this, I want to understand it. Is there a guide on this is how you set it up?
Email me first.
Okay.
I'm sorry to say that, but it's like very under active development. So
Gotcha.
I haven't yet put together a full like user guide yet.
Got you.
But I'm gonna do that tonight.
Yes. And then the third one is, if you've had other talks or talks upcoming, will that be posted to kind of see the progression or?
Yeah. So this is like the goal of this is to publish it in an academic context one day, and that's gonna be pretty hard. But that'll be on my homepage, which is right up there.
Awesome.
And I have some past KubeCon talks linked up there as well.
Awesome.
Yeah,
Well, thank you.
thank you.
Hey, great talk. I had a question since you're kind of standing in for the API server here. As a user, how much like additional like setup or like mocking am I on the hook for? You had the example of like, let's create a replica set. Like, what other setup or arrangements might I need to do to test the controller interactions under that setup?
So this simulation tool actually re-implements all of the core Kubernetes controllers. So ideally, things that you wouldn't need to do yourself in like a vanilla Kubernetes deployment, it's going to already take care of those for you. That being said, there might be always things that crop up. So as I plan to kind of continue refining the interfaces for using this, I want to make it easy to stub out and simulate things that you kind of run into.
Right, okay, and then the earlier mention of server-side apply, that's not a thing that you cover here?
I did not cover it here. I plan to implement it in sort of how this simulator handles API server semantics. Right now, it's sort of like the value is if you don't know that server-side apply exists and then you realize you need it, this tool will help you make that realization.
Yeah. Alrighty, cool, thank you.
Yeah.
So I want to ask from the perspective of an application developer which writes controllers. So generally, controllers are tested using controller runtime EN test combined with, let's say, a testing framework like Jingo. Mm-hmm. But it doesn't like provide DFS-based simulation to test deterministic convergence. So how easy is it to like convert those kind of tests to your framework so that like we can migrate from Jingo plus CNV test framework to Kamera, let's say?
It kind of depends on what the semantics of your tests are. So this testing approach is based around the specification of properties, and then the tool is going to verify that those properties hold no matter what kind of execution path you end up going down. So if your tests already in terms of properties upon cluster state, you could migrate those over. but that's not necessarily the case for any arbitrary like end-to-end test suite, like the things that Cube Builder kind of sets you up with out of the box.
Okay, so yeah, last question. Like, when will the user guide available? I really want to try it out.
Man, I really wish I could have prioritized this. Check with me 11 p.m. tonight.
I'll keep a watch.
Yeah, just start the repo. That's the best update. Yeah.
Great talk, Tim. I kind of have two questions. One, I might have missed it, but like, what was the reason for not running like a small cluster, I guess, and just observing the interaction between the controllers and the API server? Like, why have a mocked API server?
The core reason was because when I was thinking of this model checking testing strategy, I knew that an immediate problem that we were going to have to solve is this massive state space to explore. And I knew that waiting for actual containers to spin up in the case of like, test creating a deployment, that takes like the order of like seconds, maybe even like a minute. And if we have like tens of thousands of schedules to evaluate, we're going to have to like come back in 2 weeks to see what happened. So kind of from the get-go, a design goal for this project was to exploit that opportunity for swapping out the API client with some simulator client and seeing how we can use that opportunity to power more advanced model checking techniques.
Okay, that makes sense. And the second question that I had is, do you see any potential value for something like Hoverfly to observe the interaction between the controllers and the API server and then replay it to kind of fill in that simulation data, or to like be able to stub the controller behavior without having to implement it yourself? Like if it's someone else's controller and you're trying to understand the interaction between yours and theirs, do you see...
That's interesting, like kind of learn black box behavior of some controller you don't have access to the source code for. That would be really cool, definitely. I mean, I think maybe a problem in this space is that we're pulling all these controllers off the shelf, but we don't really know fully how they work, and they might conflict in ways that are hard to see. And if like you only had the binary, that's an even worse situation. So that would be a really cool use case, yeah.
Yeah, cool. Thank you so much. Yeah.